Let's go over Activity 10. So question number 1 deals with the junk data set, and it represents the word and character frequencies of emails from way back in the early 90s when junk mail filters were originally developed. So I'm going to load in the junk data frame. And if we look to see what variables we have the word frequencies of make, address, all, hour, over, etc., along with some frequencies of characters like semicolons, parentheses, hashtag, etc., and then also some characteristics of capital letters in the email. And we might wonder, okay, how well could a logistic regression model do at predicting whether or not an email is safe or if it is junk? So part A asks us to start out with the naive model, basically predicting junk or safe based on nothing whatsoever, basically majority rules. So the naive model predicts every email to be the majority level. So let's run summary on the column that has the information about whether the email was junk or safe to see what the naive model would actually do here. So I'm going to actually go ahead and in this R chunk up here do summary, the name of the data frame, $sign, and then the name of the column that I want. And what I see is that there are two levels, junk and safe. And safe is the majority level, so the naive model is going to predict every email in the data set to be safe. So it will misclassify the 818 or 1813 junk emails for a misclassification rate of 1813 out of a total of 4,601 emails. So the misclassification rate of the naive model is going to be 39.4%. So safe is the majority level. All emails that are junk will be misclassified. So the misclassification rate is 1813 over 46 over 1, and that's equal to 39.4%. All right, so hopefully our logistic regression model will do better at making classifications than the naive model. All right, so part B says that there's a particularly strong association between the probability of being junk and safe and the frequency of the word free in the email. So we'll fit a simple logistic regression model predicting the junk mail status based on the word frequency, and then we'll look at it. So I'm going to call my model M, and I'll do the logistic regression with doing GLM. Same sort of formula, y twiddle x. I'm going to predict junk based on the variable free, and that's in the junk data set. And to turn on logistic regression, I need to add in family equals binomial. So I get a warning message saying that fitted probabilities numerically 0 or 1 occurred. That's fine. It's just saying that some of those emails have essentially a 0% chance or 100% chance of being junk or safe based on the fitted model. So I can get the summary of the model, I can visualize what the model is saying about how the probability changes with the word frequency of free, and then I can also look to see how well the model does at making predictions. Alright, so we'll get the summary, we'll get the visualization, and then we'll also get the confusion matrix of our simple logistic regression model. Alright, B1 says true or false. Emails that contain a higher fraction of the word free have a higher probability of being junk. Alright, so to answer this question, what I need to do is I need to look at the coefficient of my predictor in the logistic regression model. So remember, safe comes last alphabetically, so that's our level of interest, and that's going to be the level that the model predicts the probability of. So our model is predicting the probability of an email being safe, and what we see is that that probability decreases, because that coefficient is negative, as the value of free gets larger and larger. So as free gets larger, the probability of safe decreases, implying that the probability of being junk increases. So yes, emails that contain a higher fraction of the word free, a larger value of the word free, has a smaller probability of being safe, because that's negative, and therefore a higher probability of being junk. So that's going to be true. Since the coefficient is negative, the probability of safe gets smaller as free gets larger, so the probability of junk gets bigger as free gets larger. Alright, B2 asks how many junk emails were correctly classified as junk, and we can figure that out by looking at the confusion matrix. So the rows of the confusion matrix tell us something about the actual emails in the data set. So there were 1,813 emails that were junk in the data, and there were 2,788 emails that were safe. So we're being asked how many junk emails were correctly classified as junk. Well, we look at the row for actual junk, and we see what the model predicts. We see that the model correctly predicts 638 of those emails, and it incorrectly predicts 1,173 of those junk emails to actually be safe. So how many junk emails were correctly classified as junk? That's going to be 638. How many safe emails were incorrectly classified as junk? Well, this row corresponds to the emails that were in actuality safe, and it looks like the model predicted 127 of them to be junk. Okay, so what's the misclassification rate of the model? Well, that's going to be the fraction of emails that were misclassified. In other words, the total number of errors the model makes divided by the number of observations in the data. So in this case, we have one type of error where in actuality the email is safe, but the model predicted junk. And here we have another error where in actuality the email was junk, but the model predicted safe. So if I add up those two numbers, 127 plus 1175, and then divide by the total number of emails, that'll give me the fraction that were errors, fraction that were misclassified, and that is 28.3%. All right, so not bad. We actually beat the misclassification rate of the naive model, so our simple logistic regression model definitely does much better than using no model at all to make that classification. All right, Part C asks us to check the validity of the simple logistic regression model, to check whether or not the logistic curve that the model is fitting, basically the line that we see here, provides a reasonable reflection of how the probability of an email being safe really does vary with the frequency of the word free. So one thing we can do is we can run the associate command as if we were trying to predict the junk mail status from free, and that's in the junk data frame here. And that provides us with two very rough visualizations for how the probability of each of the levels change based on the value of our x variable. So what the visualization does is it splits up the range of x values observed here, basically the range of free, into three categories here. Basically these are just zeros, emails with that didn't have the word free, emails with values of free between 0 and 0.4, so a very small fraction for the word free, and then emails with a relatively large fraction of the word free. And so what we see is that when we go to larger and larger values of free, we see the probability of safe getting smaller and the probability of junk getting larger. And this is just the same plot down here, just translated into kind of a line instead. And so we see a very rough concordance between the characteristics of how the probability is changing with free as what we would expect from a logistic regression. We know that it steadily increases or decreases with the value of the x variable. So maybe the logistic regression seems okay. We can get a more formal opinion by running check regression on our model, and this will provide us with two tests, a strict test and a pretty lenient test. So method 2 is the strict test, and very often we'll fail that, especially for larger sample sizes. We have over 4,600 emails, so it's actually no big surprise that we fail the goodness of fit test here. The p-value is less than 5%. Where we have to worry is with the lenient test. Method 1 is not very sensitive to departures from the logistic curve, and so if we fail this goodness of fit test, we really have to worry. If we fail this goodness of fit test, it is pretty conclusive that the logistic curve fitted by the model is not really providing a reasonable reflection of how the reality really is. So we see that we fail this goodness of fit test. The p-value is less than 5%. So, all right, it does not look like the logistic curve provides a reasonable reflection of how the probability of being safe or junk actually is changing with the frequency of the word free. So unfortunately, we couldn't really use this model necessarily to make predictions about probabilities and be confident in those. But our wrong model might still actually be pretty good at making classifications. And we did see that. It actually makes classifications more frequently than the naive model. We get the right answer more of the time. So while the probabilities that the model is predicting might not quite be exact, they're at least landing on the right side of 50%. We know we classify an email as safe if that probability was bigger than 50%. You classify it as junk if it's less than 50%. So basically, sure, our model's wrong. We know the logistic curve isn't really a good description of how the probability changes, but the predicted probabilities are at least on the right side of 50% more often than, say, the naive model. We're doing better at making classifications than the naive model. So, no, the logistic curve does not provide a reasonable description of how the probability changes with free, since both goodness of fit tests are failed. P-values are less than 5%. So our model is wrong. We don't want to place too much confidence in the coefficients, but even a wrong model may still be useful from a predictive point of view. And that's what D asks us to follow up on. Even when the logistic curve doesn't provide a reasonable description of how P changes, it still may make classifications more accurately than other models, than the naive model. So this is asking, is the simple logistic regression model better than the naive model at making predictions? Yes, because we saw its misclassification rate is much lower than that of the naive model. Misclassification rate is that 28.3% compared to the 39.4% misclassification rate of the naive model. So all models are wrong, which we've been discussing all throughout this class. This one is obviously wrong, but some are useful. And in fact, this one is useful at making predictions, more useful than the naive model. All right, Part E asks us to fit a more involved model, fitting the full model using all predictors with no interactions. So I'm going to use my GLM and predict junk with twiddle-dot from the junk data frame, and I have to turn on logistic regression by saying family equals binomial. And what we're going to do is we're going to look at the value of the summary. So we're going to look at the coefficients. We're going to see if the more in detailed logistic regression model provides a reasonable description of how the probability changes. And then we'll look to see how well it's making predictions. Okay, so I fit that model. I can get a summary of it. It's a huge summary because there's a lot of predictors. I can run check regression. It'll take a while because it's a pretty big model, and then I can run confusion matrix as well, and we can answer our questions. So, all right, among emails with otherwise identical word and character frequencies and capital letter characteristics, do emails with a higher frequency of semicolons have a larger or smaller chance of being safe? All right, so to answer this question, we need to look at the summary output and look at the coefficient of semicolon, because that is what's telling us essentially how the probabilities of being safe versus junk differ when emails differ in their semicolon frequencies but are otherwise identical with respect to the other predictors here. So, all right, what does the model say? Well, the model has a coefficient for semicolon that's positive, implying that the probability of the level of interest is higher for emails with larger values of semicolon. So, in a sense, what we see is that emails with higher frequencies of semicolons do have a larger chance of being safe. So, the coefficient of semicolon is positive. So, emails with a higher frequency of semicolons have a larger probability of being safe, at least according to the regression model. Now, is the difference in probabilities of being safe statistically significant as the semicolon frequency is varying? Well, we can look to see if it is a statistically significant predictor, and in fact, yes, we see that. The p-value is less than 5%. So we can say that the association between the probability of being safe and semicolon, the frequency of semicolon, is statistically significant. The p-value is 0.0035, less than 5%. Okay, so everything else being equal, it looks like emails with a larger fraction of semicolons have a higher probability of being safe. E2 says, is the variable make statistically significant? So if we look all the way back up here, we can check out whether or not it is statistically significant or not by looking at its p-value. And it's not, because the p-value is larger than 5% here. So what we see is that make is not statistically significant in the multiple logistic regression model. So basically, if I try to add in this variable to a model that already contains all these other variables, that I don't get any closer to the perfect fitting model than I would if I had just added some random unrelated predictor. Or in other words, adding make into the model with all the other predictors already in it doesn't significantly increase the amount of information that I have about the probability that that email is safe or junk. Okay, so we are asked to also fit a simple logistic regression predicting the probability from the frequency of make. So I can fit that model. And what we'll see is that we get kind of a contradictory result here. So I'll get a summary of that model. What I find is that, okay, in the multiple logistic regression model, make is not statistically significant, but in a simple logistic regression model, we find that it is statistically significant. So what's the deal? Is there an association between the probability of being safe and the frequency of the word make or not? Which of these p-values do we trust? Well, we trust both of them actually. They're both correct, but they're just talking about fundamentally different things. So what the simple logistic regression equation is saying is that knowing the frequency of the word make does, give you additional information about the probability of the email being safe or junk. However, whatever information make has about that probability must be redundant with the information provided by the rest of the predictors here. So once we know all of the other word frequencies and character frequencies, etc., also knowing the frequency of make doesn't really help us out. It doesn't yield any new additional information about that probability. So while you're not expected to answer anything here, you should be able to explain why this happens. So we do have, so there is an association between the probability of being safe and the frequency of the word make. It is significant in the simple logistic regression model. But the information that make contains about the probability must be redundant with the information provided by the other predictors. And so when we add it to a model that contains all those other predictors, we see that it is no longer statistically significant because it doesn't provide anything new about that probability. So that's why that happens. That's why you go from significant in a simple logistic regression to non-significant. It does contain information about the probability, just that information is redundant. There's nothing new when we add it to the model that already contains all the other predictors. All right, so E3 asks us whether or not this multiple logistic regression model provides a valid description of how the probabilities changes with the predictors. And once again, what we see is that we failed both goodness of fit tests because the p-values are less than 5%. So no, the behavior of how the probability of being junk and safe, how that's changing with the predictors, is more complex than what the logistic curve is specifying. So unfortunately, our model is noticeably wrong, but once again, it could be useful from a predictive standpoint. So it is not a statistically valid description of how the probability of being safe changes with the predictors since the goodness of fit tests are failed. P-values are less than 5%. Okay, now, is it useful, however? Wrong models are very often useful. Let's classify its misclassification rate. So we have a total of 122 errors, actual safe, but we predicted junk. And then we have another 194 errors where we predicted safe, but in actuality the email was junk. So 122 plus 194 over the 4601 emails. And that's going to work out to be 6.9%. So the misclassification rate is 6.9%. So yeah, while the model is wrong, it doesn't provide a statistically valid for how the probability is changing with the predictors, it's actually providing a fairly useful model from a classification standpoint. We do way, way better than the naive model, which had the misclassification rate up at about 40%, and we do way better than the simple logistic regression model predicting the probability from the that one predictor that we were doing back up earlier, predicting it from the frequency of the word free. So yeah, this model really is quite useful from a classification predictive standpoint. So the model is still quite useful for making predictions, since the misclassification rate is much lower than that of the naive model. So while the curve isn't really providing a good description of how the probability is changing, the predicted probabilities are pretty much on the right side of 50%. It's making classifications a lot better than the naive model. All right, so we didn't include any interactions in this model, and very often relationships are more complex. So very often the shape of that logistic curve, say describing how the probability changes and a particular word frequency like project, it might be a different shape depending on the value of original, the fraction of words in the email that are the word original here. Very often interactions are all over the place, and so let's consider one of them. Let's consider a model predicting, I'm going to call this mint, predicting the probability of being junk based on the frequency of the word direct and the frequency of the word you. So from you, direct, in the interaction. So that's in the junk mail data frame. And turn on logistic regression by doing family equals binomial. We'll get a summary of that model. So you just go ahead and look at it. We see that the interaction is statistically significant, so it looks like the shape of the logistic curve describing how the probability of being junk or safe, how that's changing with the word frequency direct, actually depends on what the frequency of the word you was in the data frame. So let's get a visualization of how that curve is changing. So let's visualize the mint model, and we can change the x limits here by adding an x lim equals c, and then the lower and upper limits separated by commas. And we're going to add in the legend on the left here instead of the default position. So, all right, what does our model seem to suggest for how the probability is changing? Well, actually, we see the nature of the relationship changing quite a bit. This interaction looks to be really quite strong. So, all right, F1 says, is the interaction statistically significant? Yes, its p-value is 0.02093, less than 5%. And so we can talk about, this interaction. So for what value of direct is the relationship between P and U the strongest? So, all right, we want to focus in on the relationship between P and U. So this plot here on the right. And for what value of direct is this curve essentially the steepest? So the relationship is strongest. Well, it looks like the red curve is the steepest, and the black and blue curves are pretty much right on top of each other. So we see the curve changes most quickly for large values of direct. So the red line, large values of direct, we see the probability of being safe or junk changes really quite rapidly with U. So it looks like that the strength of the relationship and the shape of that curve depends, somewhat strongly on what the frequency of the word direct was. Okay, so basically U is a better predictor of the probability when direct is large than when direct is small. Because this curve is steeper, it's a stronger relationship. F3 asks us to describe how the nature of the relationship between the probability of being safe and the frequency of the word direct changes as we consider emails with progressively larger frequencies of the word U. So let's consider the relationship when the frequency is small. Then it moves to a medium value and then to a large value. So we see that for small and medium values of U frequencies in the email, we have a positive relationship between the probability of being safe and the frequency of the word direct. So emails with larger frequencies of direct have a higher probability of being safe when U is relatively small or a medium value. But the whole nature of that relationship actually changes when the frequency of the word you is very large. We actually see that there's a negative relationship now, and in fact, emails with larger values of the frequency of the word direct have a smaller probability of being safe. So the whole nature of this relationship seems to be changing depending on what the frequency of the word you is. So what we see is that for small and medium values of the frequencies of the word you, the probability of being safe increases as the frequency of the word direct increases. However, for large values of the frequency of the word you, the probability of being safe decreases as the frequency of direct gets larger. So the whole nature of the relationship changes between probably being safe and direct depending on what level of U we're talking about, if U is small, medium, or big here. Okay, so we saw that interaction was statistically significant, so we gain additional information about that probability of being safe or junk when we add in that interaction to the model. And had we not fit that interaction, well, the whole story of how we thought the probability was changing with the word frequency direct would actually be quite different. So I'm going to refit that model with no interaction. So replace the multiplication by a plus sign. And let's go ahead and visualize that model just to see how much the story would have changed. So I should probably fit it first. So there we go. We see that without the interaction, we just uniformly assume that the probability of being safe is larger for emails with larger values of direct, with larger frequencies of the word direct in them, regardless of what the value of U is. So without that interaction, we assume that one curve fits all approach. Regardless of the word frequency U in the email, we have a positive association between the probability of being safe and the frequency of the word direct. So we would have missed out on a pretty important component of that relationship had we ignored that interaction. Okay, so question 2 changes gears, and we're going to look at the X9 store data frame. So I'm going to load that up. And what this data set does is it keeps track of what stores customers are and are not making purchases from. In total, there's a whole bunch of stores in the data frame, and in fact, we can get a glimpse for what the data frame looks like by loading it in and then kind of looking at the column names. So we have a total of actually 68 different stores in the data frame, and whether or not the customer did or did not make a purchase there. So our two levels for each one of these variables are buy and no. And so we're actually going to try to predict the probability of buying in store 68. And so unfortunately our level of interest in this case, the one that comes last alphabetically, is no. So our model is actually going to be predicting the probability of not buying. So we have to be a little careful in the interpretation. Okay, so what we're going to do is we're going to fit a model predicting the probability of buying at store 68 based on all of the other store outcomes, whether they bought or didn't from the other stores here. So what we can do is we can fit our model, GLM, predicting store 68, twiddle dot here, data equals to x9 dot store, and family equals binomial here. And so it fits it in a jiffy, and then what we can do is we can look at the summary of the model, and we can start answering some questions here. Okay, so part A says, among two shoppers with otherwise identical buying habits, so they both shop at the same set of stores and both not shop and make purchase at the same set of stores, which one has a higher probability of buying at store 68, the one who buys at store 66 or the one that does not buy at store 66? So the answer to that is the coefficient of the indicator variable representing whether or not the customer does or does not buy at store 66. And so here we have to be a little bit careful because since our model is predicting the probability of not buying at store 68, we're going to run into a few double negatives here. So I'm going to go ahead and actually just kind of write out what this coefficient is telling me. We have that the probability of not buying at store 68, that's what the probability our model is actually predicting here. We have that probability is lower, since this coefficient is negative here. So lower when basically store 66 no equals to 1 than when store 66 no equals to 0. I just wrote that out just so that I can process a little bit more easily. When store 66 no is equal to 1, that means the customer does not buy at store 66. So I'm going to replace that with when the customer does not buy at store 66, then when store 66 no equals to 0. That means when the customer does buy at store 66. Customer does buy at store 66. Okay, so the probability of not buying at store 68 is lower. All right, that's kind of a double negative. And so I'm going to just kind of copy and paste this and rewrite this. I'm going to say the probability of buying, because that's really what I'm more interested in, of buying at store 68 is higher. So I can replace that double negative just by flipping the adjectives here. And so, all right, what I have is that the probability of buying at store 68 is higher when the customer does not buy at store 66 than when the customer does buy at store 66. So I can actually answer my question now. Among two otherwise identical shoppers, which one has the higher probability of buying at store 68? Well, the probability of buying at store 68 is higher when the customer does not buy at store 66. So the answer is the customer with the higher probability of shopping or buying at store 68 is the one that does not buy at store 66. So I kind of had to reason through that because my model's predicting the probability of not buying. Then the coefficient was negative, so it was making a comment that some probability was lower. And what probability was lower? Well, that corresponded to shoppers that didn't shop at store 66. So I had a mess of confusion that I just needed to rephrase. But I find out that, all right, the customers that don't buy at store 66 have a higher probability of shopping and buying at store 68. Okay, so we can go and move on to part B. We can look to see how well we make predictions here. So let's look at the confusion matrix of our model. See what kind of errors that it's making. And what we're going to do is we're going to comment on whether or not the multiple logistic regression model is more useful than the naive model for predicting whether shoppers buy at store 68. So we're going to look at the misclassification rates. So the naive model, how is it going to do? Well, the naive model is going to predict everything to be the majority. So we look in actuality, 470 shoppers made a purchase at store 68, and 1,030 did not make a purchase at store 68. So the majority did not. So the naive model is going to predict that everyone did not make a purchase at store 68. So that naive model is going to make 470 misclassifications. So 470 out of that 1,500 results in a misclassification rate of 31.3%. Okay, well now about our model, the multiple logistic regression. What kind of errors did it make? Well, in actuality, we had those 470 people making a purchase at store 68, and the model correctly predicts 221 of them to make a purchase there, but it predicts no for 249 of them. So we have 249 errors, and then other types of errors where in actuality the customer did not make a purchase at that store, but the model predicted that they would. So 249 plus 122 out of the 1,500. We can get that, and we find that that is 24.7%. So yeah, this multiple logistic regression model is much more useful at making predictions than the naive model. The misclassification rate goes from 31.3% down to 24.7%. So the model is more useful for making predictions than the naive model. All right, so is this a statistically valid description of how the probability changes? Well, we can run check regression to see how well our model does from a statistical point of view at describing how the probability is changing. And in fact, in this case, both p-values are bigger than 5%. So yeah, it does look like from a statistical point of view, this model provides a reasonable reflection of reality. So the model does provide a reasonable reflection of how the probability changes with the values of the predictors, since both p-values are bigger than 5%. We passed the goodness of fit tests. Okay, so this last question, question 3, asks us to read in act10-account.data. So what I'm going to do is I'm going to read this in and call this account, so read.csv, And I'm just going to go ahead and copy and paste the file name here. And I got that. So it's a pretty big data set, 32 observations, 48 different variables. And what we're going to try to do is we're going to try to predict the probability that a customer makes a purchase of a new type of account that a bank is offering. So specifically, we're going to fit a model that predicts that probability. So predicts purchase from checking balance. So checking balance and branch of bank with no interaction. That's going to be in the account data file, and turn on logistic regression with family equals binomial. So boom, we got that model. And the overall goal is to see, is the probability of opening up that account different between the different branches of bank. So let's compare otherwise identical customers in terms of checking balance. Is there a difference in essentially conversion for the different branches? So some banks have more success than others. So we can run drop one to determine whether or not the branch of bank is statistically significant in the regression model. So if I do this, what I find is that the p-value of branch of bank is much less than 5%. So yes, it is statistically significant. So why is that important to us? Well, if I look at the summary of the model, there's a lot of different branches. There's actually 20 different branches of the bank. And so I want to know if there's any difference in the probabilities of getting customers to make that purchase between those 20 different branches. And the results of drop one are telling me that yes, there are. Remember, I don't look at these individual p-values because that's only comparing the probability of this particular bank, say B14, to that of the reference level, which is B1 in this case. So yes, there is a statistically significant difference in probabilities, and let's determine which branch has the highest probability from the output of summary. So, okay, well, looking at the summary here, I'll include that. What this coefficient tells me is the the relative difference in probabilities between the bank represented by the indicator variable and the reference level. So in this case, the reference is B1. And when I see a positive number, that means the probability of the level of interest is higher for this bank than for the reference level, bank 1. And so what am I actually predicting here? That's something I should have checked. Well, if I look to see, what the data looks like, account $ purchase, what are the levels? It's no and yes, so I'm predicting the probability of having that customer make that purchase, buy into that new account. So it looks like bank 10 has a higher probability than bank 1, bank 11 has the lower probability than bank 1, etc. So what I need to do is I need to find the most positive and most negative coefficients. And so that just involves me scanning up and down through this list. And so for the positive ones, this one is 0.13. And I'm looking at all the other positive ones, see if I have one that's more positive. I'm not seeing this because these are all 0.0 something with the times 10 to the minus 2. So actually it looks like branch 10 has the highest. So we have that branch is statistically significant since the p-value in the effect test is less than 5%. And it looks like branch 10 has the highest probability. Its coefficient is most positive here. Which one's most negative? All right, well, here's a negative 1.08. Here's one that's negative 0.9. That's pretty negative here. Minus 0.6, minus 0.4, minus 0.06, minus 0.19, minus 0.09. So it looks like this is the most negative here. So B14 has the lowest probability. Its coefficient is most negative. Okay, well, we can visualize the model to actually see all the implicit logistic regression equations. It's not going to be too useful because there's so many different branches of bank. It's going to be actually hard to determine what color is what. I'm going to move that legend to the bottom right here just to see this curve a little bit better. But this kind of magenta looking curve looks to be the very lowest, and that seems reasonable. That could be the color of B14, which is what I predicted. The color looks a lot like B4, so it's kind of hard to tell the difference. Which one has the highest? Well, it's really hard to tell. I said B10 did. B10 looks like a red line, and if I look super closely here, then, okay, maybe there's the red line being the highest. So I got to get the coefficients to really make that assessment. So without an interaction, which we didn't put in that model, we assume that one logistic curve fits all. Regardless of the branch of bank, the shape of the logistic curve, describing how the probability of opening up that account changes with checking balance, looks the same. That may not be the case. Maybe there might be a stronger relationship for some branches, a weaker relationship for others. So it's a good idea to, incorporate that interaction. So what I'm going to do is actually just copy and paste, since I'm pretty much going to do the exact same thing here. Just change this plus sign to a multiplication sign to add in that interaction. So I'm going to check to see, is that interaction statistically significant? And yep, here's my interaction, checking balance times branch of bank. So it is statistically significant. So what we see is that the interaction is statistically significant. P-value is less than 5%. The implication is that the shape of the logistic curves are going to vary between branches. Not all branches have the same curve. So, all right, let's actually just look at the visualization of the model. Actually, the summary isn't going to tell us too much. Remember, whenever we have interactions involved, the numbers don't really say all that much. We really just have to look at the regression lines here. So let's visualize this model and make some comments. And okay, well, the first thing that is immediately apparent to me is that one of the banks actually has a negative relationship between checking balance and the probability of opening up that account. Which one is it? I'm not sure. It could be B11, B19, B9. I'm not going to worry too much about that. And I'm just going to say that I see that one of the banks has a negative relationship between the probability of opening the account and checking balance, whereas the rest of the banks have positive relationships. And I do see that some other banks have very strong relationships between checking balance and the probability of opening that account, very steep logistic curve, whereas other ones are relatively shallow. So among the other banks, we see that sometimes the strength, or sometimes the relationship between the probability and checking balance is strong, the curve is steep, and sometimes it is weak. The curve is, or changes slowly, let's say. So for that black and that gray line right there, it's changing pretty slowly. So yeah, it looks like that interaction is a pretty important effect. It's definitely statistically significant, and we do see a pretty big difference visually between the shapes of the logistic curves between the banks. One bank really stands out for whatever reason. It seems to have a negative relationship. All right, so that is our activity 10.